Okay, Assalamualaikum. So now we are going to discuss about biopolymers related to forensic science. Okay, why biopolymers? We have to understand first because this is the starting materials that lead to semi-synthetic polymers, and then to understand further on how people can synthesize organic polymer based on what have been uh, research in the biopolymers. So biopolymers related to forensic science is largely related to the exoskeletons of insects and arthropods. Okay, so part of your course we learn largely on the analysis of um, chemicals and also the determination of PMI and cause of death using larvae. Okay, part of what will be discussed in biological aspect and also forensic evidence, I think. Okay, so you have to understand what makes the exoskeleton of these arthropods and insect for you to understand better how to analyze them later. Okay, so biopolymers will start on the discussion of polysaccharides. Okay, polysaccharides is the biopolymer. Okay, is already polymer that contain a lot of disaccharides. Okay, so what makes disaccharides? The starting monomer is glucose. Okay, that contain carbon 6 and 6H2O. So this is the open ring conformation of glucose, which we call as Fischer projection, but we can also have the closed ring conformation Haworth projection. This is the one that will be used along discussion, because this will show you what is the projection. Is this an alpha glucose or is this a beta glucose? So alpha and beta will determine the composition and also physical properties of polymer. Remember in previous video, I said that physical properties is very important for you to understand. The simplest polysaccharide is your table sugar, okay, disaccharide, whereby the monomer is from glucose and fructose. But how they bond together? So how they bond together is the one that we have to understand. Is this a beta glycosidic bond or alpha glycosidic bond? Okay, in order to understand that, you have to remember your organic chemistry. But don't worry, we won't go that much into organic chemistry. I try to make you understand as much as possible. Okay, so this is how Fischer projection of glucose turned into Haworth projection, which we call as hemiacetal form. So you can see that the carbon is denoted as 1 starting from here, 1, 2, 3, 4, 5, and 6, and then this 1, and then after the acetal portion over here will rearrange themselves. Okay, we will get 1, 2, 3, 4, 5 like this. So in order to make this carbonyl group, okay, stable, okay, it will be changed into OH part over here with the elimination of NH. So this is the part that we want to identify whether this is alpha or beta. Okay, so this is the carbon number 1 that will involve in polymerization. Okay, most of the time. Okay, by just looking onto this, okay, we will have two type of conformation. One is chair conformation. If you can see over here, our OH is on a plane like this, while and this is what we call as equatorial. Another one, chair conformation, is where your OH is axial down. Okay, so this is what we call as beta and alpha. Okay, alpha, remember, is down, beta is a plane like this. Okay, so this makes this carbon as an anomeric carbon. Anomeric carbon means that is a stereo center. What is stereo center? Okay, dimer. Okay, now let us see on the resulting structure depending on which type of anomeric carbon and how they will interact. So the first possibility is sucrose. If you see from the sucrose over here, okay, three possibilities shown here. The first one is sucrose. It is between a glucose monomer and also a fructose monomer. Okay, so from the glucose, the carbon 1 is in the axial coordination because the OH is down, and then it is attached to the beta glycosidic on the fructose over here. So this is alpha glycosidic linkage on glucose and beta glycosidic linkage on fructose. Okay, and both are anomeric C. Remember the stereoisomer. And then the second one is gantibiose. It's between glucose and glucose. C1 on the first glucose is having equatorial, while the C4, while on the C6 of the second glucose is here. So we have one 6' linkage, and this is beta glycosidic linkage. Just now is 1 4', right? Okay, because it's related to the fourth carbon. Okay, so this is what gantibiose is having 1 6' linkage, and the last one is lactose between between a galactose and a glucose. Galactose over here, and also glucose. So glucose is on the fourth carbon and the first carbon of galactose. So this is 1 4 glycosidic. Why beta? Because the OH from the first galactose is equatorial. Okay, so usually beta over here is according to the first sugar that is linked. So, and then we go to saccharide-based biopolymer, important for forensic science, especially here. This is largely related to the exoskeletons of arthropods and also insects. So, chitin. So, chitin is a tough polysaccharide found in the exoskeletons of the insect and arthropods such as the maggots. The monomer is an amide form from the replacement of carbon in glucose. It's supposed to be carbon here, right? It's carbon number 2. Sini. It is replaced with an amide bond. So we have this NH, and then we have this carbonyl. Okay, therefore we have amide group. Because of the existence of this amide group, it can form the tough polysaccharide. The main skeleton of the polysaccharide is still the same. Okay, you see that we have the C1 over here, and then C4 over here, C1 over here again, C4 over here. The only difference is that the amide linkage at the C carbon number 2. Okay, this is carbon number 2, carbon number 2, and carbon number 2. And this is a beta 1 4' linkage because the OH on the first C is equatorial, OH tadi. And the linkage is between C1 and C4. And this is a beta. And because of the carbonyl group formed on the amide, it can form strong hydrogen bonding, okay, with the NH over here. Therefore, it is giving you a very tough chitin polymer. Okay, chitin is the outer skin of your maggot. That's why when you want to analyze the chemical component in maggot, you have to think of how to get rid of this chitin first. Okay, because it's very tough polymer, therefore it needs special acid or base condition. Okay, forensic entomologists examine insects found in a corpse to identify drugs or poison. So you have to think of how to digest or how to get rid of this chitin skin. Okay, you have the you have the maggot, and then you have the exoskeleton of this maggot kan outside. So these are the exoskeletons of this one. Sometimes when they go into fly phase, it will leave out the skin. Okay, the second polysaccharide related to forensic is starch. Okay, starch over here is a glucose-based polysaccharide. Okay, it's a glucose-based polysaccharide. So this is glucose monomer in hemiacetal position. Okay, starch is okay, starch is the starting material or starting monomer for different kind of something like glycogen that usually available in animal, whereby animal use this excess glucose or glycogen to use as a kind of energy storage. Okay, so if you see from here, we have alpha 1 for linkage, and then can also be branch. Okay, remember a polymer can also be branching with alpha 1 6 prime. Okay, to make a polymer branching like this. So the other component of starch are amylose and amylopectin. So this is a linear amylose, okay, and this is branch amylopectin. What are the differences between them? Okay, so if you see from here, the difference is between this glycosidic linkage and also the additional of alpha 1 6 prime glycosidic linkage in amylopectin. Okay, this is branching. So amylose, okay, is linked by this alpha 1 4 prime linkage, can also allow from linear to be a form of helix, something like this. So this amylose is a very bulky starch group, okay, and it makes up 20% of the starch itself. And amylopectin in the different side of it is linked both by 1 4 prime and also 1 6 prime, giving the branching like the very organized branching over here, and therefore it make it insoluble. Why insoluble? Because more OH parts in amylopectin is being used for polymerization, while in amylose you still have abundance of OH to be available for any hydrogen bonding with water, but in amylose less of the OH left. Okay, so that makes it insoluble. Remember about the hydrogen bonding. The size of amylopectin can reach up to million monomers. So example problem over here. How forensic biologists use starch gel to perform electrophoretic separation. Okay, I'm not sure whether you are in capillary electrophoresis topic yet in forensic analytical chemistry, but this is gel electrophoresis, whereby this gel is used to separate molecules. So we will see how starch can form a gel matrix. Okay. So this is gel, this is porous link, everything. So how it can turn into something like this that can trap component A, component B, and component C depending on the size. Okay, because of the helical structure, and remember amylopectin just now can also provide you the branching of the polymers, and therefore it will provide hydrogen bonding with water up to certain extent lah, because we have less hydrogen OH left for water. If you are using amylose, it's even better to have solubility with water. And when it is swelling, it can form a semi-rigid structure, and then can enable the separation of these molecules according to their porosity and also molecular weight. The next polysaccharide, very important to forensic science, is cellulose. Okay, cellulose is the starting material for fibers. Okay, what kind of fibers? Naturally occurring fibers from cottons, from jute, from can also make up paper and so on. So we have to understand cellulose. Okay, cellulose is structurally similar to amylose. Okay, whereby it contains the 1,4' linkage, right? Okay, over here. Okay, it's a beta one. This linkage over here can also, okay, enable hydrogen bonding from the remaining O. Okay, sini. When you have this million polymerization, means that the N is up to 1 million, for example, you can have cellulose microfibril just like what available in the plant cell. Okay, so imagine that in the structure of this cellulose fibril, when we take out this one, it is actually made up of millions of polymer. Okay, cellulose can be found in plants, of course, and as the structural support in plant over here. However, even though it's a glucose polymer, animal and human cannot digest cellulose because we don't have the enzyme beta-glycosidase to break the linkage. Okay, so this cellulose is also of interest of paper production, whereby they modify the lignin, hemicellulose, and cellulose found in the woods, okay, and they classify it as lignocellulose complex. This lignocellulose compound imparts strength and varying different types of rigidity of the plant. Okay, for example, wood sample contain 40% cellulose, and cotton contain up to 90% of cellulose. So wood sample 40% cellulose, and the rest of the wood is based on other materials. Okay, so cellulose in wood structure has a pseudo crystalline structure. Remember, if it's more towards semi-crystalline or crystalline, its structure is more rigid. Okay, it's more rigid means that the composition of the cellulose is more organized, and therefore the bonding is also better, and lignin and hemicellulose can bond them together better as well. So here you can see organized structure of cellulose, the green one, okay, attached to the lignin by hemicellulose. Okay, lignin, the red one. Okay, so hemicellulose is a saccharide-based biopolymer composed of subunits of glucose, galactose, mannose, and xylose. The most common subunit is xylene. Okay, this hemicellulose constitutes of 25% of wood solid. This is how xylene looks like. Okay, it's the same as well. This special arrangement of cellulose can also makes up the cell wall of the biomass. Okay, so lignin, in the other hand, is the one that is least well characterized. This is the lignin, the red one. How this is mixed up? Okay, if you see, it can contain phenylpropyl. This is the phenylpropyl. Okay, linked by strong single bond C here, that is resistant to many degradation pathway. So that's why when you want to analyze wood sample, for example, lignin is the strongest complex cellulose that you have to think of how to get rid of it if you want to have something in the cellulose over here. Okay, when a plant decompose, lignin, this one, the red one, will produce humic and fulvic acid, and this is the precursor for peat and coal formation. Yeah, when extracted, lignin has a glue-like consistency due to their function of gluing and the strong bond over here. Okay, so next one, example of cellulose is cotton. Okay, cotton over here is a natural fiber. It is subunits of this one, same one. And cellulose is also the derivative of semi-synthetic rayon and semi-synthetic viscose acetate that we will learn in the semi-synthetic subtopic later. Cotton is cotton in overseas is produced from seed fiber. Okay, the one that we have in Malaysia is in the cotton pod, right? Like this. I think the tree, if you ever see it, is a very big tree. Okay, that contain a lot of cotton pod. It's a green color if you ever see lah. So cotton is the one most encountered in crime scene. Okay, as exhibits or evidence. Sometimes is the most commonly found, therefore sometimes evidence usefulness is not that high. Yeah, it's just to classify certain case and also to shorten the horizon of finding things. Okay, so it is easily identified by PLM, the microscope. Okay, because we can see cotton properties like a spiral one. Okay, this one, remember? So it's very spirally as compared to polyester. Polyester is really straight. Okay, and there is no flakes such as the wool. Okay, wool is coming from the animal, right? So it's not flaky like wool. It is not straight like polyester. So cotton has a very distinctive feature.